Okay. The floor is yours.
First of all, I'd like to thank you all for asking me to give my serpentine path to where I am. If Melinda would please give the next one. Yes. From the very beginning, determinism was thought to be the will of God. And even 100 BC, there was this quote from Ecclesiastes that it was pretty agnostic. You wonder how it got into the Bible. It says, I returned and saw under the sun that the race is not to the swift, nor riches to the scholars. That means don't go into science for the money. But time and chance happeneth. And even before Ecclesiastes, Euripides was a Greek. He was very unpopular in Greece, so he went to Macedonia. But he has this recurring character in most of his plays called Talthybius. And after getting one horrible assignment after another, Talthybius finally loses his patience and screams at the heaven, great God, do you look at man and care? Or do we seek order in the chaos when random chance alone rules the mortal sphere? You've heard the phrase, order out of chaos. This is where it comes from. But the whole point of this was that randomness is bad. And that was the idea for over 1,000 years, I would say. And if Melinda would give me the next one, please. Anyway, the first time, to my knowledge, that randomness was actually considered a good thing was in the 19th century. I mean, there were works before that, how do we handle it, mostly having to do with gambling. But Ludwig Boltzmann, and on the left you see his gravestone from the Vienna Central Cemetery with S equals K log W, W meaning the number of states in a system, and that's the entropy. And he came up with his famous equation, Boltzmann's equation. And if F, which is the density of the W over on the left, the distribution function has the convective derivative, P over M being basically the velocity of the whole system, okay? And then you have external forces, and that's all being balanced by the collisions between all of the molecules in a gas or the stars in an elliptical galaxy, whatever. But the whole point was that this was the basis of a lot of astrophysical research. When I started my graduate studies, are you going to believe this? I actually started my graduate studies in 1975. Well, in 1979, after I got my doctorate, master's, and was working on my doctorate program, I went to my oral qualifiers, and I was trying to do the statistical mechanics of elliptical galaxies. And an elliptical galaxy looks like a blob, as you can see on the lower right-hand corner. But what happened during my oral qualifiers was that I actually got into a bit of a dispute with my advisor. By the way, this is not a good idea. And he thought that I was way too emotional to be a scientist and recommended that I not be advanced. But everybody did pass me unanimously against the recommendation of my advisor. But it was difficult for me to find an advisor after that, because after all, this was a powerful guy in the department. So basically, the job I could find was in underwater acoustics. Now remember, this is 1979, okay? And if you will go to the next one, please. You will see that at the time, that was in the large, just basically the height of the Cold War. And in underwater acoustics, you have, no, the advisor was actually, Prigogine was a nice guy in comparison. Anyway, so the thing is that later on, you'll find that all of the villains will remain anonymous, and I will name the heroes of this story, okay? So anyway, what happens is in the ocean, the sound speed has a channel. You have basically the temperature, which decreases, and the sound speed decreases with it, until the weight of the water on top of it actually balances the temperature being decreased. And then in the isothermal depths of the channel, it increases. So what happens if you have a source in, let's see, can you see this? Somebody give me a thumbs up or down. Anyway, so if you have a source in the channel, was that up or down? Anyway,
it was up.
Sound will actually try to stay at the minimum of the channel. Now, at the time, the Soviet Union had these submarines that didn't go quite this deep, and they actually weren't yellow. But they did have titanium hulls so that they could go below this sound speed minimum. And what the American Navy wanted to do was to see if there was a way that this sound could be scattered up into the upper regions of the ocean, where the United States could put sensors. Well, the thing is that there was scattering, and you could get a signal, but what happened then was that I still wanted to do stochastics. And by this time I had found stochastic differential equations. I saw that Charles During is on here, and he will remember us going to Werner Horst-Stemke's class when he was writing his book. Anyway, so what happened was that I told the Navy, I wrote a proposal and asked, maybe we might be able to see if this sound can be scattered up into the upper regions. Now, if we have the next slide, this is probably, this and the next one will probably be the 4 slides of this talk, okay? So the thing is, say I have an equation where F is slow, S is slow, and eta is fast. Then there's a central limit theorem, which is not your grandmother's central limit theorem. It is not the one that was, this is de Moivre or Laplace after that. What it is it shows that in the limit, as the size of eta gets very large and the time scale of eta gets very small compared with the time scales of F and S, you get a stochastic differential equation in a scaled time scale. So say eta works on times of t, and t, say it's nanoseconds. And let us be centuries. Well, there are a whole lot of nanoseconds and centuries, so epsilon squared here is going to be very small. So in the scaled time, you can treat x as obeying a stochastic differential equation of this type, where W is a Wiener process. Now, a Wiener process is a Gaussian random variable with variance proportional to time. And when I say that it has a little dot here, that means that it's in the sense of Stratonovich, and I'll tell you what that means in a minute. But I want you to notice that you can't just use the coefficient here. The time scales of your fast system go directly into your equation through this equation phi, through this term phi, which is not the lag covariance matrix. What it is the low frequency intercept of the spectrum. Okay, so this is the central limit theorem that we now use to justify stochastic differential equations. And if you go to the next slide, you will see this horribly complicated thing that looks like it has the deterministic dynamics here. It has the coefficient of the noise in it. Notice this little red square with the alpha. That means that you treat it in the sense of Stratonovich if what we are doing is approximating a multi-scale system as a white noise driven system. Otherwise it's zero. And then we have the diffusion. You don't have to look at all the details, just know that you have conservation of probability. And so anyway, basically I showed in my dissertation that yes, you would get a signal, but it was completely useless because you couldn't tell where the signal was. And so the US Navy hated this result, and they said it was too mathy anyway, so go ahead and publish it in the open literature, which I wanted to do anyway. And years later, I was working with a couple of people who happened to be in the Russian Navy at the time. And they said, you know, Cecile, as soon as that paper came out, we were using it. You saved us a lot of time. To which I said, wonderful. Well, I did not want to disappear into the classified research. So what I did was I went to the Max Planck. And that's where I was working with Klaus Hasselmann, and I learned to work with Hans von Storch. And after a while, if we could go to the next one, please. They had come up with this thing called principal oscillation pattern analysis. And there are these two papers, Hasselmann, Pips and Pops in 1988. And then there's another paper, von Storch et al. In 1988, showing that if I have a discrete linear process like this, I can get the eigenvectors of this G with a combination of the lag covariance and the equal time covariance matrix. And by taking the eigenvectors of G, you could see which patterns were most likely to be important in the system. Well, what I did then in what became linear inverse modeling, and at first I used to call it POPs because I thought, well, this is just a trivial extension of POPs, but then Hans really kind of objected to that, saying it was different. So, okay, it eventually became known as linear inverse modeling. That if I have an equation that's in the continuous part like this, and so I make the assumption that this white noise psi is related to a Wiener process, as is this, then I can also not only get the principal oscillation patterns, but I can get everything that describes the system. I can get L, I can get the variance of the stochastic forcing. I can get everything. Now, these two views can actually describe the same system. And if they do, then this matrix G is equal to the matrix exponential of L tau. And not only that, the noise in the pop formulation is equal to a convolution of the deterministic and stochastic noise. Okay, so there is a connection between these two. So if you go to the next one, please. Long story short, although that might be a little late, we can get a complete description of the system, including L and the S and S transpose. You cannot identify S uniquely. If you see that I put the identity matrix in between those S's, then any orthogonal matrix will actually satisfy the conservation of probability. But you can get L, you can get S, and then you can make predictions of the whole field with this trivially by making G times the initial condition. And then there are actually tests for the original assumption of linearity. Basically, you can get the Green's function, which is what this is if it is a continuous process, from only one lag. And if your predictions don't change at other lags, I mean, you can generate the Green's all other lags given the Green function at one lag. And that's a test of linearity. Okay, now, what's the next one? That's what I was afraid of. This is difficult. We eventually had to go back to the United States. Eventually, we wanted to go back to the United States. And these were rather turbulent years because we were trying to find jobs in the United States. By the way, this is the slide that my boss's boss told me that it would be interesting for you guys to listen to. So just listen. I applied for a job at UCLA in the math department. And one of the villains of this story realized that my husband was also on the market and said, "Oh, you guys are back. Alex," that's my husband's name, Alex Garcia. "Do you want to take this job your wife applied to?" My husband, Alex Garcia, he's a hero of the story, said, "Cecile, what do you want me to do?" Well, at this point, we couldn't really, neither of us was employed. So I said, "Look, go ahead and take it." So anyway, he took that job and I was able to find a lectureship in a much smaller university in physics. When I got there, I found that the chair was making the secretaries' lives miserable to get them to sleep with him. He would be fired now, but not then. So I was having secretaries falling into tears in my office. He would never touch a family member, but he was making, you know, I have a pretty thick skin. I mean, you know, it didn't really matter that he was making all these offensive comments. But trying to rape the secretaries was pretty serious. And so the vice president of academic affairs asked me to put into writing what was going on there and what my experiences were. And at the end of the year, the chairman was no longer chairman, the dean was no longer dean, and my life was miserable. Enter Michael Gill. Ta-da-da-da-da-da. He said, "Cecile, you know, you don't have to stay there. You can come and work at UCLA under me if you can get a grant funded, and I will help you do that. So he did. He helped me get a grant funded, and I had 1 year with Michael at UCLA, and he helped me get a couple of papers published, and I was really very, very grateful to him. Now, years later, I was telling this story to in front of Michael, and Michael said, "What? I had no idea you were going through all that." And I said, "What do you mean? You said that it was because of it was not fair." And he says, "Yes, but I meant because your husband didn't have your job. I mean, had been offered your job and had no choice but to take it." So anyway, that actually made me feel even more grateful because he was willing to go to all this trouble without it being such a horrible situation. But it was a horrible situation. So I did have a year to find another job. And after putting out about 100 applications, I got nothing. But I did go to the AMS, American Meteorological Society meeting once, and I had behind Maurice Blackman at the beer line, and we started talking, and he asked me to send him a CV and Boulder making sea surface temperature forecasts. So that's the whole story of these miserable several years. Now, next one, please. Before I was making El Nino forecasts and they were pretty skillful. But then my husband, Alejandro Garcia, said, "Cecile, you know what we can do? We can verify Landau-Lifshitz 1948. Well, what that was that Landau and Lifshitz had said that the Navier-Stokes equations could be augmented with stochastic terms representing the individual molecular collisions in a gas, and that they should have a certain temperature dependence. So my husband is a molecular dynamicist, and so he did a molecular dynamics simulation. I put linear inverse modeling. You know, what happened is that it had thermal boundary conditions on the top and the bottom, and it had slip boundary conditions on the side. And he would just let it go, and molecular dynamics, they would all go and collide and all of this stuff. And he separated the thing into 100 different regions and gave me discretized time series of u, that is horizontal velocity, meridional velocity, and vertical velocity, and also using local equipartition temperature. So I applied linear inverse modeling, and lo and behold, what does LIM give you but the Navier-Stokes equations, the linearized Navier-Stokes equations. But the important thing was that we were able to get the covariance structure of the stochastic noise due to the individual molecular dynamics, collisions. And so on the left side, what you see is a landscape and contour plot of the variance of the one component of the velocity, and it's the diffusion term, okay? So we got the diffusion term really nicely. And we also got the temperature dependence of the variance, the lines being the Landau-Lifshitz theory and the dots being what LIM gave us. So this was a nice application of LIM. And I wanted to show this to you because I don't think this is really appreciated. Okay, but to be honest, I was getting paid to do El Nino forecasts. So let's do El Nino forecasts. Next one, please. First of all, let me talk about some work by Brian Farrell in 1986 and on, who showed that if you had a linear system, and I'm not really talking about a linearized system, although it does affect to that, but their eigenvectors are not orthogonal, you can get temporary growth. So look at the top, and let's say I have two eigenvectors of the deterministic dynamics, one of which simply decays, and the other one, that's B, and the other one, A, which actually not only decays, but rotates. Well, if the eigenvectors are constantly orthogonal, then the sum of A plus B has to decay, all right? If each eigenvector decays with time, so does their sum. Now, when the modes are not orthogonal, like on the bottom, A is just like the same A in the top, but C is the same length as B, but is off to this, catty corner to it. And the sum, A plus C, actually can increase with time, okay? So this is temporary because after all, what happens at long times is everything decays to zero anyway, but you get growth. And this was the theory between what could happen with sea surface temperatures and why the sea surface temperatures would work. Predictions would be skillful. So if you look at the next, you will see the paper that came out, The Optimal Growth of Tropical Sea Surface Temperature Anomalies, by me and Prashant. And this happened, this paper was born when Prashant and I, after, thank God, I mean, the talks didn't start until 9 a.m. And not only that, it was in Asilomar, California. And so that meant that it was a time zone earlier. So that meant that we didn't have, neither he nor I are morning people, all right? I'll go into my idea about how the minority of night owls should be given affirmative action later. But anyway, the thing is that he said, well, you could take your Green's functions that you're using for your predictions and do the same thing that Brian Farrell is doing. And so, yeah, so when we got back, we did that. And on the left, what you see is the leading eigenvector of the right singular vector of the Green's function that we were using to make predictions for El Nino. And it peaked out at about 7 months and then decayed. The filled circles are what you would expect for the error variance. So we were saying, okay, we probably shouldn't expect any predictability of El Nino past about 14, 15 months. And I do believe that that is still what all people can predict. I don't think there are any predictions that are valid, skillful past a little bit more than a year. But the eigenvector associated with that eigenvalue, by the way, it's the logarithm of the average error energy growth versus the logarithm of this leading eigenvector. And you can't see my hand. So this eigenvector here, this is the log. And that corresponds to this pattern here, which doesn't look anything like El Nino. But if you put the Green's function onto it, it actually evolves into what looks like the full-fledged El Niño 7 months later. Not only that, these forecast errors that we got really didn't depend on the lag at which we got the parameters for the Green's function. So that was a pretty strong indication that El Niño is in large part linear. Now, I'd be the first to say these are all approximations. And when we say that it's a linear process, we're saying that it's approximately linear, that the nonlinearities can be treated as a combination of yet another linear operator plus white noise. Okay, so this came out in 1995. And I think I'm almost done. After that, if I can go to the next one, and this should be a very busy, yes, it is. You don't have to read this, obviously, but this was some work that I did with James A. Hansen. That means it's the Jim Hansen that didn't get his fame from studying global warming, but rather the Jim Hansen that was searching for Somali pirates using probabilistic techniques. And one thing that we discovered was that if you really wanted people to take seriously a really mathy thing, you had to entertain them. So the point is that if you're going to generate a stochastic differential equation, you really kind of have to be very, very careful with the numerics. And we showed a cautionary tale when people were not careful with the numerics. But the only problem with that is that there was a paper by Cloden and Platten that said, okay, but if you do a stochastic generation, you have to have a teeny tiny little time step, which is about 500 times smaller than the time step, than the smallest time scale of the deterministic dynamics. So what all of this was using the Faust legend to introduce a way of using the central limit theorem. This open book here is actually the same limit theorem that I showed you with the picture of de Moivre. And what happens is the general C.M. Faustus tries to possess the saintly stochastic parameterization and sells his soul to the devil for numerical facility. And anyway, the two archangels, data assimilation and central limit theorem, come along and save the day. And so at this time, this was a way of being able to integrate a stochastic differential equation using a much larger time step. So this is what this thing was about. Now, we always keep trying to improve LIM. And one of the things we did was try to say, well, what happens if you have not additive, multiplicative noise? Hi, Christian. I know Christian was working with MIDA in a while, so I hope you're not offended by my next slide, which Melinda will show. And so what happened was that we had what's called the CAM noise model, which is this equation 1, and I think you can actually see that. But anyway, there had been an attempt to guillotine this result. And by saying that you couldn't get a linear multiplicative system by using a homogenization procedure, because you couldn't get the linear term without also having a cubic term. Well, as it turns out, that turned out to be the starting point, that they had used a different starting point. If you use a different starting point in a nonlinear oscillator, you actually can develop through homogenization a CAM noise model. So that's all this is saying. And basically, this is another one of our tale of two scalings. It was the best of results. It was the worst of results. It was the white noise limit. It was the no noise limit. The variance exploded. The variance vanished. In short, some of its noisiest authorities insisted on being received for good or evil in the superlative degree of comparison only. And so the conclusions were that is a far, far better thing we do with data than anything we ever do with assumptions. But there are issues with both descriptions, but you can get a CAM noise system as a limit of a nonlinear oscillator. So this was another thing that we did in order to extend it. One thing that we've also been doing is looking at cyclostationary versions of this. To be honest, I've lost interest in them because, come on, I've been doing it for 35 years. And the fact is, okay, 33. But the fact is that I'm more interested now in stochastic parameterization and in rigorous developments of stochastic parameterizations using the central limit theorem that I showed you. So I think I've come to the end of my talk. If you will go to the next one, where there are no conclusions because the story's not really over. I have no intention of retiring in the next few years, and there's still a lot of stuff I want to do. But I'd be very happy to answer any questions you have, and I actually came in on time. So you can stop recording, right?
Thank you, Cecile, for this very nice and inspiring talk from several point of views. We heard a lot about the past. Can you tell us something about the future? Where do you think that the future evolution of this field is leading?
Okay. I think that the stochastics are now entering a golden age. They really are, because with the work of Tim Palmer and others, it's basic. There's no way we are ever going to have a general circulation model at the molecular level. All right, it ain't gonna happen. And yet every time we get higher and higher and higher resolution, we find that we need even finer resolution in order to get processes that are affecting the weather and the climate on the timescales that we're interested in. So this means that stochastic parameterizations have to be things that we use. Now, the central limit theorem that I showed you assumes that there are systems, that all of the systems have finite variance that you want to treat as white noise. And there are other systems which do not have finite variance, but they still exist in nature. And so I think that basically stochastic differential equations driven by Levy processes will have to be used and used well. I think that rigorous developments of stochastic parameterizations from the observations And that's one thing I have to say that I really like about physical science lab is that not only do we do theory, but we are also involved in uh, experiment and basically field campaigns in order to get the data that we need in order to get stochastic parameterization. And in order to see how the stochastic parameterizations improve the forecasts, as most of you know, this is a very long-winded answer to your question, but the fact is that forecast models right now do not have sufficient diversity in them to be able to give a decent estimation of the uncertainty of a forecast. And so that's why people wanted to put in stochastic parameterizations in the first place. However, what people are also finding is that not only does it improve the forecast uncertainty, it improves the signal of the forecast. It improves the ensemble mean. And that's exactly due to the noise-induced drift. If you remember that little red square that I had in my conservation of probability, that's completely due to that term. So I think that what's going to be happening now is the marriage of deterministic general circulation models and rigorous stochastic theory to develop stochastically inclusive general circulation models. I think that's the way things are going.
Thank you.